And so the exercise today was to look at some more kind of artificial gene expression data. And in this data, we have a case where there's 16 genes and they're grouped into logical groupings of 6 genes, and random truth tables or random logic gates have been generated for each grouping of 6. So actually there are 8,008 possible groupings of 6 genes out of 16 possible genes. So this is the number of kind of abstract or hidden layer features that we're kind of thinking about having to model. And the task here is to deal with 3 underperforming neural networks that have been set up, but are each performing poorly or as well as logistic regression in a case where we're expecting the structure and the data to be represented by a neural network better than what you would achieve with a logistic regression. So we're looking for a receiver operating characteristic that gets us above this orange line here. And so if we look at network 1, the solution here was that there are too few hidden layer features. So we have this network architecture here with 32 nodes, and we mentioned that there are 8,000 features, abstract features, or 8,000 groupings, logical groupings. And well, maybe we don't need 8,000 because they're weighted randomly, so some are more important than others. Nevertheless, this is still too many to be represented accurately or to get good performance with just 32. So that was one thing. And then the other thing was that the regularization parameter here, so we have in this network regularization turned on. So this is L1 regularization that we covered. And this is the lambda parameter, or this scale factor that is being used to determine the strength of regularization. So the larger this value is, the more harshly parameter values are being penalized. And if this is too high, then you're going to underfit. So that's what's happening here. So this should be a couple orders of magnitude smaller. The second network had the issue of overfitting. So if we looked at the loss function getting printed out, we had these extremely low values. So if we remember back, there's this key number 0.693. And so we're well below that, meaning that this is almost a perfect model. It's predicting with almost perfect accuracy the training data, and so that is cause to be suspicious, actually. And then if we look at the training data versus validation data, so if we partition our training data and set aside some for validation, we see that actually the validation loss function is going up. So the model has been getting really bad, actually, as early as, epoch 20 or something like that here, despite the training loss function continually declining here. And so how could you fix that? So the solution was kind of set up there already in the third network. You could implement early stopping in that case to deal with the overfitting. But so what was the problem with network 3? The problem was the learning rate was too high. So we had this problem of bouncing around and failing to settle into the basin at the end. So if we kind of fixed all these little things, had enough nodes, implemented early stopping, we could get a network that was performing better than the logistic regression curve here. We would see that the validation loss is going down and never going up, which is what we like to see. So what were the features of this network? So we had more nodes, not quite 8,000, but 800 nodes, a single hidden layer here. We had dropout layers implemented, so we're turning off some of these nodes to avoid overfitting. We also have early stopping turned on to avoid overfitting. We have the learning rate turned way down, so that we have this smooth, kind of steady approach towards the minimum, and we're not likely to be bouncing around too much. And we have mini batch sampling as well turned on, again, to avoid overfitting.